robot is able to present using a PowerPoint presentation, and it can ask quiz questions. So this is part of a concept where we want to develop a robot teacher. So in the back you actually see something looking like a teacher with a school board, etc. So I guess if we have those props, we should actually put them on. This is kind of an early demonstration that you see. And if you have any comments or reactions or expectations that you would have with such a robot, please tell us, and we would be interested to know what you think about it.
Hello everyone, good afternoon. My name is TuDelft. Today I will be taking over the lecture for a short while. Throughout this presentation I will show you some of my skills. I will start by showing you my body and talk a little bit about my hardware. We will end this presentation with some trivia questions. I have two cameras with which I can see everything in high definition. This allows me to see the world around me and even recognize people and objects. I can't even see all of you here right now. Interesting. You there, on the front. You weren't sleeping, were you?
No. No.
Using my 4 microphones, I can recognize the location of where sound is coming from.
Yeah.
If I try my best, I can't even recognize the words that you say. As you can see, unlike many robots, I can walk with my 2 legs and grab objects with 2 arms, just like you can. I can't even sit down if I feel tired and stand up again, but I am not as good at this as you are. In fact, if I am in a good mood, I can't even dance a little. All right, that is enough exercise for now. Oh yes, time for a little quiz. How much do I cost? Let's see. Exactly, that is correct.
So who said 16 and who said 160,000?
Well, it's the only bird that can fly backwards.
Wow. Oh. Sorry. Goodbye.
Let's see what you thought. Yes, exactly. Very good.
Hummingbird. What is that?
How much sand does the Sahara Desert consist of? This is a trick question. Let's see. Sounds logical, but it is mostly rock. The correct answer was 20%.
What?
20.
What freeze?
Eva is a prototype of a home care robot, and the basic things of her is to do the fetch task in your house at the home care for the elderly people, and she can right. With her arms she can pick some drinks off the table. This robot can't talk, but to show her emotions, we add sound, light, and eyebrow expressions. Now she's angry. She can be sad, and she can be confused. So if she doesn't understand the task, then this light will show the emotion. She can also do person falling weeks ago we had a little accident, so I can't show you that things. So if you want to ask anything. Yeah, we built it with 6 guys. One of electronics, 2 of mechanical engineering, 2 of software, including Hans, and 1 of industrial design.
So maybe you could tell a little bit about how you actually developed it and what key motivations were for this kind of design?
For our project, we get the base and the gripper, and the rest we had to design by ourselves. First thing we did, I think, was designing the complete robot to see what kind of emotion brings it to a person. The industrial designer designed it that way that it has a little bend backwards, so it won't scare a human when it rides towards it. Also make a head that doesn't look like a person. So maybe you know there is the theory of the uncanny valley. When a robot looks more like a human, we don't accept it anymore. So we keep it at the robot level. Furthermore, about the design.
This robot doesn't have any actuators.
No?
It's just 2 pendulums. Okay, so the idea is that you look into mechanisms and really simple mechanisms like this, try to understand how people walk. And the idea is to invert the double pendulum. So what you do is you just, as a human also, you just swing one leg forward and then you catch yourself on one foot, use that impulse to swing the next. And the only thing where your knees, for instance, come in is to clear the ground. Also you have some movement at your hips, but usually you're just swinging 2 pendulums and being stable, and you don't care too much about every detail. And if you look at like robots from Japan, you would see them walking with bent knees and being really careful with each step, trying to be stable in each configuration. And what we did here is just make a system which is robust. Well, this system is quite unrobust because it's just 1 pendulum, but if you would add some actuation to the system, which we later did, you can see that it's more robust, and because and I think this is one of the most interesting in our lab. It's also doing the swinging motion. It can walk on a flat surface, and it has knees. And I actually have it right here. So what this one does is really simple as well. And it can walk quite a bit, quite a long distance, just on one pressure can.
How much energy would that consume for, say, a kilometer of walking? Because that's one of the main problems now, because you're saying this, if it walks quite a distance on a canister of compressed air, how much energy would that be?
Do you want the number in joules or what?
Well, just wondering.
Well, if it's not comparable to what we do as humans, because we have a more efficient energy system in total. But I would say it's at least in tens of times more efficient than the robotics that you would use with other algorithms. And this one, you can see it also tilting a little bit, and it has this abduction degree of freedom. It can take turns, cannot. This robot is actually a little bit more stable in this direction, but still won't be able to make turns. And when we made this one, we were actually also involved in a project called RoboCup. Anybody knows Robocop?
Yeah, the movie.
Yeah. Uh, so but they also have a humanoid league, so they have bigger robots, and we made Tulip, which is on the far side there. You can see the black robot with kind of triangular upper body, and that one has even more degrees of freedom, and which would make him capable of standing up, doing the split, because that's a known tactic. If you try to, if you're the keeper and you want to just stop a ball, you just make the split, as the robot can. That one is also capable of doing extra rotations. So in theory, it's stable enough, and it has the degree. Projects, for instance, with pneumatic actuators attached to your shoe. And what it basically does is it gives you a little push, so plantar flexion torque around the ankle. So it gives you a little push off right at the front leg, right at this moment.
That means it assists the back muscle.
Yeah, your calf muscle. Yeah, exactly. Yeah, and mostly the soleus. So I'm not sure if you guys are into the whole. Okay.
No, not the muscles.
Huh? Not the muscles.
No.
Okay. But what happens is that you have a few muscles which are responsible for push-off, and in this case we wanted to see a reduction in activity in the soleus, because that one is actually, like the name already tells you a little bit, it's just solely spans the ankle and the lower leg, while the gastrocnemius, which is also there, which is the biggest muscle, is actually attached to your upper leg also. So it's also generates a knee flexion moment. Still on one? Okay, it's almost finished. Yeah?
I have a couple of questions about
Yeah?
this system, just because of myself.
Mm-hmm. Passive. So you see me here. Let's see if we can put a break somewhere when I'm in. Can't follow. Okay. So you can see here the structure around my legs, right? And it's a passive structure. So we try to figure out a way to do it smart mechanically, to store and release energy. And what happens here is that I have right down here I have a spring which can generate a torque around my ankle. Here I have this harness which is coupled to a linkage mechanism which can generate moments around the hip and the knee here, flexion moments. And what I do is during the touchdown of my leg, I actually store energy in this system, and in push-off and some other phases, also swing phase, I regenerate it. So I try to fit basically an extra spring which spans multiple joints, which stores energy and generates energy in a smart way. And this is actually passively present in the walking mechanism. So we try to look at the dynamics of walking and then fit a tri-articular spring in it. So the upper harness and all these things here. It has abduction, it has hip flexion, knee flexion, and this is passive. Because putting this weight here, like we already discussed, it's devastating for your efficiency in walking. So you can see
This
the
been
exit.
in the news last year.
It's quite recent, but yeah. Actually, all around the world, these exoskeletons are popping up, and
Wow.
so here it's just swinging with some signs on it. That's me testing it. This is unactuated, so I have to back drive the actuators. So it's really heavy for me to walk, but this is just a demonstration of the range of motion it has, and can see that you can sit down with it even more. And next movie you'll see that it's actually a patient test.
There are sensors in the head.
Oh yeah, this is a project called Mindwalker, and it's actually aimed to make a coupling. So it's for people who have a paraplegic, are paraplegics. So they usually suffered some injury, and we selected ones which has some control over the torso, and which has some control over the torso, but don't have any muscle activity down from there. But the brain is okay. Usually, brain is okay, unless they have suffered some head injury. But usually, that part is quite okay. So what we can do is we make the coupling. So this is such a patient. It doesn't have the cap on because this is just a trick of balancing. So the control here is it shifts
Wow.
to one leg. This is still quite primitive test. I think they've done the more successful ones. This is in Italy with one of our partners.
And this guy has some injury why you can't use
Yeah, I
the
think
muscles.
I think this guy it was T6 or T5, so it's really high. We
What's
didn't
it
even
called?
select those. Oh, sorry.
What's a T5?
Even wervels. Dus, dus als je bijvoorbeeld hier een opening zet gewoon, dan is er overal, en bijvoorbeeld hier is het vanaf je buik uit tot je benen. En bijvoorbeeld in je nek, dan is eigenlijk bijna alles wel veel.
Yeah, so it originates from a spinal cord injury, and they have this numbering system, which the higher you go, like I said, we selected people with like lumbar, spinal cord injuries. It thinks it has to stand up again. There it goes. This one is called Leo. And Leo can learn. This was a PhD project. So let's give it a little push. That's like that. Okay, now he wasn't really learning, but he's quite robust to really small changes. But the idea behind Leo is that he can learn his own properties and even make him learn to walk itself. So he just start from scratch, lay it down, and then it knows general parameters about this environment. It knows its own state space, and it's trying to so we're trying to reinforce it. So every time it does something which we desire, we reward it. Every time it does something like falling or misstepping, we punish it. And if we do that consistently, usually rewarding is a little bit better, even for robots. Then it starts to learn.
Imagine rewarding and punishing a robot.
You just give it a unit. So we call it a cookie, but it's just the name we give it. So it's basically an optimization algorithm. in which you let it do some random action and see if it's the desired outcome. If it is the desired outcome, you give it a credit for it, and then it will try to mimic this. And you give it a little exploration factor, so you can give it a really huge exploration factor and it will do lots of random stuff, which doesn't really give the reward. We can give it a really small exploration factor, and then it will start really doing one task that rewards him a lot. So if it just we've seen it a lot that we've done a step up, so it just has to do this, and then if it does this, it even gets a reward. And if it starts doing this, then it gets lots of rewards. It's not the full action you want, it's just about the action you want, and it gets a reward from it. So it starts doing something really simple, which is not what you want, because you didn't give it an exploration factor. And if you give it a slight exploration, which is a robotic hand, and this hand has one motor and 6 degrees of freedom. So what we do is we use some gearing here in between and some linkages to make one motor move multiple degrees of freedom. And we try to get the behavior right by tweaking the distances and lengths of the bars and linkages. And then you'll be able to move 6 degrees of freedom in a specific order, of course, with one motor. And the nice thing about it is that the environment actually decides on how the mechanics will work. For instance, when I put my hand in here, it will do this. But if I put my hand like this, it will do something different. So we'll do lots of different objects. It can do lots of different grips, depending on what you put into it. So that's again trying to get the mechanics right, and doing actually the control a little bit earlier in